I'm here live with Dr. Shep Doeleman, who is a friend of the show, past guest on the show, talking about the previous phenomenal discovery by the Event Horizon Telescope. Today's announcement really shook up my universe, the universe of those who care about monsters and incredible gravitational discoveries. But Shep, take it away. What did your team announce today? This is so phenomenal.
It was a pretty incredible day, Brian. So today we announced the first image of the supermassive black hole in the center of our galaxy, Sagittarius A star. It's at the same time very similar, but also quite different from the black hole we imaged in 2019. That was M87, which weighed 6.5 billion solar masses. So let's first talk about why they're the same. No matter how you light up the space-time around a black hole, the intense gravity dictates what the image is going to look like. So these black holes are surrounded by an ultra hot plasma. It's radiating light across the electromagnetic spectrum, and it's bent by Einstein's gravity into this ring shape. So the fact that we saw a ring in M87 and we saw one in Sagittarius A star, which are different in mass by about a factor of 1,000, is another confirmation of Einstein's theory of gravity, that these black holes all bend light in exactly the same way and appear the same. Now they're different because M87 is a monster. M87 is one of the biggest black holes we know of in the universe, and it has a jet that is powered by the black hole, piercing the entire galaxy. Whereas Sag A star is the timidest of eaters. It is just eating a tiny, tiny amount. At the press conference today, Michael Johnson said that if Sag A star were a human, they would be eating 1 grain of rice every million years or so. I mean, that's the rate at which Sagittarius A star is delicately consuming the gas around it. So it's not a monster. What makes it so special is it's our monster. And we can use its proximity to study it in a way that we can't necessarily study M87. So it's a great day for black holes in that they're the same, but also that we have a completely different black hole to study now.
And the shape of the black hole, it looks, I was kind of anticipating this would be about the black hole, the Milky Way galaxy, but the shape and the morphology looks so radically different from the M87 black hole. Is that purely attributable to its mass?
Well, it's partially the mass, but also mostly at this point, it's due to the fact that Sagittarius A star weighs 1,000 times less. So that means that the dynamical time scale, the rate at which it changes is 1,000 times faster. So while we're observing Sagittarius A star, it's changing while we're trying to capture its image. That means that the quality of the image is poorer. It's like trying to capture a running person in a time exposure, a long time exposure. It gets very blurry. So the fact that it looks a little different, but there are blobs around the ring, is mostly a consequence of the fact that it's changing while we're looking at it. And not so much that it's intrinsically much, much different. Now, this is a good thing, right? Because this tells us that when we want to, when we talk about making movies of black holes, we now have our leading actor, right? Sagittarius A star is the one that we want to make a movie of because it changes on these very, very short time scales. For M87, we would take snapshots every few weeks and tie years of observation into a time-lapse movie, but Sag A star we can see evolve in real time. So again, the images are a little bit different, a little bit the same, and it all speaks to the fundamental physics around black holes.
Will we also expect to get more information in the coming years from this black hole? Or are you still taking data with the EHT currently on this object?
Yeah, absolutely. So for example, we've learned some things right away from this treasure trove of data. First, 4.5 million solar masses are within the photon orbit, right? This is the strongest evidence for the existence of the supermassive black hole in the center of our galaxy, full stop. In 2020, Reinhard Genzel and Andrea Ghez won the Nobel Prize for determining that there was a compact object at the galactic center. But the Nobel Prize Committee stopped short of saying it was a black hole. Now we have the proof, the long sought proof that the object at the center of our galaxy is indeed a black hole. There's no other way for us to get that particular ring that matches the mass derived by Gensel and Gez at 4 million solar masses. Everything fits together now. It paints a wonderful picture. But you asked about what comes next and what we're learning. So for example, looking at the simulations of black holes, we can now say that there are likely strong magnetic fields operating close to Sagittarius A star. We can say that the temperature of the electrons is probably pretty high compared to the temperature of the ions. It's something that people who study accretion are very interested in. And we can also say that the time variability seems to match generally what we might expect. It's actually, Sagittarius A star seems to be a little quieter than all of our computer models might suggest. So when you run these computer models on banks of CPUs, they predict that Sagittarius A star would be a little more jumpy, a little more frantic, a little more puppyish. And the Sagittarius star object that we actually observed seems to be a little calmer. So that's something for us to really dig into over the coming years. And we have data in the can from a couple of other epochs, and we're building the instrument out all the time. And the next generation EHT will make true movies of Sagittarius star.
Yeah, I want to get to that in a bit. I noticed you have a new button on your lapel. You had a previous one last time. So if people can find your lapel manufacturer, then they'll be able to get data, in real time. Just kidding. But in seriousness, when we look at the black hole image from M87, and we look at the black hole now image that you produced with your team from the Sagittarius star, we see, there's no scale. There's no way to tell just from the lapel pin, are they the same size? Of course they're not. This one is maybe 500 times less massive. But what do we learn about the sense of scale and perhaps the orientation, because the black hole, could be in any orientation? And was it just fortuitous that they seem to present the same general morphology, and they're circular? Obviously, there's a shadow, there's a dark spot. Was that fortuitous, or is that something else?
Yeah. So, you've hit the nail on the head there, Brian. So it turns out that because the ring seems to be roughly uniform, or like the north of the ring is as bright as the south part of the ring, there are lumps, but there's no clear asymmetry from one side to another of the Sagittarius star result. That tells us that we're probably looking at it face on. And that is very interesting, because consider for a moment that we live in an outer arm of the Milky Way galaxy. So if the spin of the black hole was aligned with the rotation of the Milky Way, we would be looking at Sagittarius A star edge on. It does not look like we are seeing an edge on black hole. That means that the black hole, for some reason, seems to be pointed not far from our line of sight. Now that's a mystery, and that's what we're going to have to resolve over the coming years. Like, why is that? There's a little bit of evidence from the optical and infrared groups that suggest also that we should be seeing it face on. So this is consistent with that. But another mystery, like, why are we in this preferred direction from the galactic center? So that just speaks to your question about why it kind of looks the way it does. But in terms of scale, now let's talk monsters, Brian. The M87 black hole is 6.5 billion solar masses. It's the size of the entire solar system. Our entire solar system could fit many times over in the shadow of that black hole. So to keep that in your mind for a moment, Sagittarius A star, though it appears the same size on the sky because it's closer, is actually about 1,500 times less massive. The event horizon and shadow of Sagittarius star would fit well within the orbit of Mercury in our own solar system, right? So you're looking at something that snugly fits close to the sun versus something that could swallow the solar system many times over. And the fact that we're seeing these black holes that appear the same size reinforces the idea that black holes are the same no matter what size they are, no matter what mass they are. The ones that discovered by LIGO that are at 10 solar masses seem to be the same as the ones, the Sagittarius star, which is 4 million solar masses, and one that's 6.5 billion. There's no other object in the universe that exists in a single form at all those different scales. If you took a mouse and you tried to scale a mouse up 1 billion times, it would collapse under its own weight, right? I mean, a mouse can't be 1 billion times the size of a mouse. Its skeleton doesn't scale properly, right?
That's
but
right.
A black hole is perfectly at home no matter what mass it is.
That's incredible. Yeah, they are the biggest objects, single objects in the universe. They've been around for a long time. I made a video on my channel today where I talked about, could they make up for the dark matter in the universe? And before we get to that, I want to ask, behind me is a picture, I'll put on that side, of M51, which is the Whirlpool galaxy. It's a galaxy not unlike the Milky Way, but M87 is an irregular or elliptical galaxy. It's very different. Could that be in part why we see these blobs? Are these the blobs that Andrea and Reinhard call, these A2, and are those blobs that we're seeing in the image, are they any way related to the clumps of gas and dust and star forming and star dying regions in our galaxy? Or are they completely different?
Yeah, they are very different. It also helps to make a jump to the scale here. So the tremendous pioneering work by Andrea Ghez and Reinhard Genzel showed the orbits of stars around an unseen mass, that compact object that we talked about earlier. And the closest point of approach to those stars is still about 1,000 times bigger than the shadow we observe today. In other words, if Newton saw the motion of these stars around the black hole,
right,
he would not be surprised. You have to look very, very carefully at the motions of those stars to discern any hint of Einstein and general relativity. Whereas we're so close that everything is governed by tens of billions of degree gases emitting light is bent like taffy in the gravity of the black hole. So totally different origin of those blobs. We're much, much closer by a factor of about 1,000.
Amazing. I want to ask a question that, lay people want to know. Oftentimes people ask me, what do you, hope to see with the Simons Observatory or any other project? And I always say, I don't like to think about what I hope to see, what I want to see, because that can lead to confirmation bias, et cetera. In this case, you must have known for a long time that this was going to happen, and you must have been excited to see it in some sense. Talk about how did this emotionally resonate with you, if at all? We scientists are human beings, despite the stereotypes to the contrary. How did this culmination of your planning with your colleagues for decades and fighting for funding and fighting for scarce resources, how does it feel to make this image of something that would blow the minds of someone as great as Einstein or Newton or anybody? How does it feel just on a personal level? I'm curious.
A lot of different emotions are running through us, like awe, humility, relief, and inspiration. You said something very interesting about Einstein and how his mind would be blown. The more I've been in this game, and I've been chasing Sgr Star for over 25 years now, the more I think about it, the more it's about connections. We have a connection historically. I call it the 100-year handshake with Einstein and Schwarzschild. We're continuing their tradition. And every day we talk about the Einstein equations. Every day we talk about the Schwarzschild radius. It's not a fabrication, right? It's not posturing. Like we dip into those deep traditional scientific wells every single day. And to be able to take the next step like this with this amazing team is a fulfillment not just of my personal dream, but also of the dream of all scientists, that we will all build on the work of each other to address these big questions. So it's being part of a 100-year process that gives the depth of it, the richness of it, the texture of it. That's what I find most comforting and most incredible about this whole journey. That and being able to work with this team. I mean, the people involved in this project are just incredible.
And you talked about the future. Let's go before we get to the future for the next generation, which I'm thrilled to hear about. When we spoke last time, it was in between. I spoke to Heino Falca and others about the polarization results. Can we expect polarization results from the Milky Way galaxy's black hole, Sgr Star? And if so, what will that tell us?
Yeah, absolutely. We already know just from some of the brightness not the polarization, but the brightness, that there are likely strong and ordered magnetic fields around Sagittarius A star, but we haven't mapped them yet. That will be the next project for the EHT. That, and then looking at even more data with better arrays. So right now we have a hint that things are changing. In fact, we know they're changing. We can see from the raw data that things are jumping around, but we can't form a movie yet. We cannot make a movie of Sagittarius A star. So it's like we know something is moving, can't make it out. But in the future, we'll be able to advance our algorithms and build out the array to capture that motion. So over the coming years, we'll look at new data sets, look for polarization, but also look for this motion. And that's what differentiates M87 from Sag A star. We'll be able to catch the black hole in motion with Sagittarius A star. So that's really what motivates us to build the next generation EHT.
Will that have more to teach us about astrophysics when these movies are made, or will it teach us more about gravity, or all of the above?
So it turns out both. What we're really after is kind of twofold. One is, how do these black holes launch jets, and how do they interact with the matter that's circling them? And understanding that will tell us how black holes feed, how they're in symbiosis with the galaxies that host them, and how they can disrupt potentially star formation in those galaxies. In other words, how the large scale structure that we see in the night sky evolves. At the same time, we know that these rings that we see have substructure. Some of the light is gently bent to us, but some does a U-turn, some does a full orbit around it. With the next generation instruments, we hope to be able to tease out that first ring. And that will be a much stronger test of gravity, because the light that does a U-turn around the black hole spends more time in that highly curved space-time. So the photons that make it to us have a lot more information about whether that space-time conforms to Einstein's theory, or whether we have to find a new theory.
Can we go back to what we talked about on your first visit on the Into the Impossible podcast? I'll put a link to that conversation up here, over here somewhere. And that was about the next generation. Surely, any reasonable funding agency would see these results, including the M87 results from 3 years ago, and now these, as harbingers of incredible new science that's uniquely capable by this instrument and this instrument alone. First of all, I've been told the best thing in business is to have a monopoly. Do you guys have a monopoly? Is there any other team that can do what you guys do? And so is there, or is there not, an alternative for the NSF and the ESO and so forth to upgrade and build a bigger, better version of EHT?
Well, so what I would say is that there are some different views on how to proceed to enhance the EHT. But the one that has been, endorsed by the National Science Foundation, and the one that was written up in the Decadal Review that just came out. This is this navel gazing exercise that all of U.S. astronomy engages in every 10 years. And they wrote that the next generation EHT concept that we put forward is viable and should proceed. So we're damming the torpedoes. Like, we're just full steam ahead to do this. And, observing at multiple frequencies, adding different colors to our palette when we image these black holes, widening the bandwidth with bigger sensitivity. Hold on one second.
Yeah. I know you have to go soon.
No, I just have to, you're doing all these things and building out new telescopes. That's a very robust path ahead. And we already are working with private foundations and the NSF to do that. I really just see no showstopper here. I think that we should set our sights on 2030, make high dynamic range images of M87 to show the energy extraction from the black hole through the jet, and on Sagittarius A star to capture the dynamics during a single night and test Einstein's theory by looking at orbits of matter. These are the questions that will motivate us, physics, astronomy, even history, philosophy, and mathematics for the coming decade.
Oh, for certain. What about adding new baselines? I mean, if you put one at the North Pole, if you put one in space, what are the limits to the resolution, both in space and time and frequency of the current suite of instruments, and then think big 100 years from now. What could you imagine we could do with a next generation EHT?
Yeah. So I'll have to go after this just
Yeah.
because I'm being raptured.
I'm sure you have a busy day.
Yeah. But so the magic of interferometry is that the number of baselines you can use, the number of connections between antennas, each single pair gives you one data point. That number of pairs goes as n squared. So it's quadratic. So every time you add a new dish, you get many more baselines. It grows very, very fast. So even by adding 6 new dishes, for example, we would triple the amount of data that we're going to get. And if we were to add, many more sites than that, we would again go up by a factor of 3, so that by 2030, we should be 10 times more capable than we are now. Now that's a new telescope. Anytime you have an order of magnitude, you've broken through a certain barrier. So when you ask about new baselines, that really is the trick. Filling in the Earth-sized virtual lens, that'll take us to the next step.
That's unbelievable. Shep, I want to thank you and give you congratulations, a hearty congratulations to you, your team, your friends in Europe and Asia, all around the world. This is a worldwide effort, and we need it more than ever. I mean, you think about what unites people and what divides people. Who cannot fail to be just moved, blown away, and excited about the future of technology, human capital, and these resources that you and your team have spectacularly unlocked. Thank you so much, Shep, for sharing your time. I know you got a huge day ahead of you. Congratulations, my friend. We'll talk again soon.
Okay, bye, Brian. Take care.
Bye, my friend. Bye-bye.